everyone, and welcome to DSC 494 or 598 Grasshopper. I'm Biaina Bogosian, and I'll be your professor for this course. So I'm trained as an architectural technologist and a computational designer. And what that really means is that I use computation, data, and different emerging technologies to address questions in architecture, the built environment, and the relationship between people and the spaces they inhabit. My work sits at the intersection of design and technology. I use algorithmic design to generate and sometimes evaluate architectural form. I use robotics and digital fabrication as well to rethink how we build. I'm also currently in ASU's Media and Immersive Experience Center where my lab is and where this robot sits. And what I do is I use immersive media like augmented reality and virtual reality and large-scale media to create new ways of experiencing environments. So I'm very much excited about environmental data, simulation, and anything that has to do with technology. Sometimes that's software and sometimes that's hardware. But at the core of this is my interest in rethinking the way that we respond to climate, ecology, and how we shape human behavior. Across all of these areas, Grasshopper has been one of my primary design environments for over almost 18 years, and that's since the platform was first released. I've used it to drive robotic 3D printing or different stacking approaches using different robotics, to control adaptive building facades, to build interactive installation that responds to people in real time, to run environmental simulations, or to visualize urban data using geographic information systems and other approaches. So it's a really, really great and powerful tool. And I want to be clear about something, which is Grasshopper is not just a learning tool or a toy for making interesting shapes, but it is a real productive tool for us to really begin to think about how our data and environment could be brought together. And when you eventually reach its limits, and at some point you might, basically using computational and parametric thinking that you will develop during a course like this, it will directly help you to move on and use more robust workflows and tools, and whether that's Dynamo in Revit or any other sophisticated programming environments. So let me take a step back and talk a little bit about what we actually mean by some of these terms. I've been throwing around terms like computational design, computational thinking, parametric design, algorithmic design. So what do these really mean and what's the relationship between them? So computational design sits at the intersection of two really critical things, which is computational thinking and computational tools. On one side, you have computational thinking, which is about the reproduction of information through interactions, breaking a problem down into logical steps, defining relationships, structuring sequences of operations. On the other side, you have computational tools, and this could be software and hardware that enable representation, analysis, synthesis, and evaluation. And where these two meet is computational design. Now, if we zoom out a little bit further, computational design itself sits within a larger landscape. It draws from computer science, which gives us algorithmic design and computer graphics that allows us to simulate, do calculation, and the ability to write explicit step-by-step, basically operations that generate or evaluate form. And it draws from design thinking, which gives us the practice of designing with parameters. In this case, we can define variables and relationships that shape a design rather than shaping the geometry directly. When all these things overlap and come together, you get the full picture of computational design as it is practiced today. And some of this might be still abstract, but I'm hoping that along the semester, as we talk more about this, hopefully these terms and these overlaps could become more hopefully clear for you. So where does Grasshopper fit in this history, right? So as I told you, I've been using the tool for almost 18 years. So is that the beginning of the spectrum? Is Grasshopper one of the latest tools? So let's talk a little bit about this timeline of the history. And of course, depending on who you ask, this history might be slightly different, but it's still very new and still evolving and developing as we speak. So for decades, architects used computers primarily as drafting tools. So this is where the term computer-aided architectural design, or CAD, comes from, right? So maybe you've used AutoCAD before, so that's where CAD comes from. And CAD was really about digitizing what we were already doing by hand. So for instance, you drew lines, you extruded shapes, then you produced documents, right? So computer-aided approach or processes, it allowed us to automate this process, right? Then began the shift in early 2000s with the emergence of parametric and algorithmic tools. In 2007, David Rutan at Robert McNeil and Associates released the first version of Grasshopper. So McNeil, maybe you're familiar with the company, maybe when you already downloaded Rhino, you came across that, but Bob McNeil or Robert McNeil is the person who created Rhino. And Rhino was initially created as a tool for jewelry designers or people that wanted to do precise 3D modeling using NURBS geometry type. We'll talk about NURBS further in our courses, and NURBS, that's a term that stands for non-uniform rational B-splines, and basically it's a mathematical way of defining geometry that's infinitely smooth, right? And that's maybe what you came across when you're using Rhinos. If you zoom in, your geometry is infinitely smooth, right? So that allows you to do very precise modeling for certain type of things, in this case jewelry, right? Because people were interested in designing very fine shapes. So Grasshopper in 2007 was introduced within this Rhino ecosystem by David Rutan, and originally it was called explicit history. And this term is really important, explicit history. So basically, when you're creating a series of steps or an algorithm, you're explicitly defining its step. And you're going to hear that from me very many times, which is, let's try to explicitly define our steps, then build our Grasshopper definition, which is basically the algorithm that we develop within Grasshopper environment. So again, Grasshopper was introduced in 2007 as a plugin within Rhino. And the idea was radical at the time. Instead of modeling geometry directly, you would build a visual, basically graph of your logic or a network of components and connections, and the geometry would be generated from that logic. It made algorithmic thinking accessible to designers who had no programmatic background. And that is still what makes Grasshopper so powerful today. It bridges the gap between design intuition and computational rigor. You can see your logic, you can trace how data flows from input and output, from left to right, and you can understand why a form looks the way it does because you build the rules that generate that, and you're able to go back and trace that. So explicit history, which was the term that originally Grasshopper was called, it allows us to trace history. And in the next video, I'll talk a little bit about this idea of recording history in Rhino and how that became Grasshopper. So we'll cover that in our next video. Now, in terms of geometry, Grasshopper works with two fundamental types that you will use throughout this course. The first is the NURBS geometry, which I mentioned earlier. That's non-uniform rational B-splines geometry, which stands for, as I said, a mathematical way of defining your geometry that's infinitely smooth using splines. And these are ultimately very precise curves and surfaces that Rhino is built on. and they're very accurate in terms of the type of operations that they allow us to do. The second is mesh geometry, which represents surfaces as a network of triangles or basically four-sided polygons, right? So we're working with polygons. Meshes are what you encounter in renderings, in 3D printing. So when you're, for instance, converting your file, you might be asked to submit an STL file. An STL is a file that is basically compiled as a mesh. And meshes have their own advantages and NURBS have their own advantages. And throughout this course, I'll talk a lot about also geometry. So for us to really understand Grasshopper, we need to understand Rhino. And for us to really understand Rhino is to really understand how mathematically our geometry is constructed. And then we add this logic of computational thinking in order for us to create variations of geometry, right? So in this course, you will work with both and you will learn when and why to use each one. But you might still be asking, why should I learn this? Why does parametric modeling matter to me, right? So, well, if you have ever used conventional 3D modeling software like Rhino or SketchUp or even Revit, you are probably used to modeling by following a sequence of commands. You create a shape, you extrude it, you move it, then you subtract something from it, and you end up with a form, right? And that is fine for a one-off design, right? So you're trying to try something and you're able to do that. But what happens when you need to make a change, right? Your professor comes to your studio and they're saying, well, what if you slightly add this? Well, then often you need to start from the beginning and hopefully you saved your initial curves and then you go through this operations again. But what if your client is asking you to do 10 different variation, or that's not very sustainable, right? So in conventional modeling, you're either undoing or redoing, or you're starting all over again. And that's a huge waste of time, and we shouldn't be doing that. So parametric modeling flips this entirely. Instead of modeling the object directly, you design the rules and relationships that generate the object. You build a logic, a set of instructions, right? And then the form comes from that logic. If you want to change something, you change a parameter within that logic. That could be a number, a slider, and that entire model updates instantly. So this means you can explore dozens of design variations in the time that it would take you to manually rebuild one. And that speed of exploration is transformative, right? Especially in the early stages of design when you're making the most important decisions about size and shape and orientation and performance. And sometimes it might take you a little bit longer to write the algorithm versus just drawing something and extruding it. But here we're talking about workflows that allow you to ultimately, over time, evolve and create variations. Sometimes maybe you need to look at the trade-off, but trust me, once you have a nice clean algorithm, you can use it for many different things and even plug it into many different. So you might develop these libraries of code or Grasshopper definitions, and that's what we call a Grasshopper file or a Grasshopper algorithm, that eventually you can connect it together and create more sophisticated relationships. So that is what parametric design is about. It is not about making complicated shapes for the sake of complexity. It is about giving yourself more control, more options, and more intelligence in your design process. And once you learn to think like this, the concepts transfers everywhere, whether this is maybe you want to transfer to Dynamo for Revit, it's exactly the same logic, right? You're using a visual algorithmic editor, which is node-based, and you're just changing maybe the specifics of the software, or Houdini, which is another great node-based, let's say, algorithmic modeling, or Fusion 360, or even writing your own algorithm using Python or C#. And all of that is also possible within Grasshopper. So you can either use kind of standard Grasshopper components. Components are the elements that allow us to take input and create output, or you can create your own custom using programming. So it's very exciting and very flexible. So in this course, we will start from absolute zero. No prior programming or Grasshopper experience is needed. You might not even be very comfortable in Rhino. I'm hoping that maybe you have some prior understanding of Rhino, but even if you're a beginner in Rhino, don't worry about it. Not only I will provide supplementary material if you want to brush up your Rhino experience, but trust me, through understanding Grasshopper, you're actually going to understand Rhino better. Because, as mentioned before, we're going to really understand fundamentally how geometry and different data are created, which is going to really reinforce the way that you think about geometry and design in Rhino. So we're going to have 7 modules, and that's the 7 weeks that we have in this course. And through these 7 modules, we will go from the basics of the Grasshopper interface and geometry all the way to site analysis. And we're going to end up creating a parametric tower together. We're going to create a facade for that and apply environmental simulation and animation to that. And I'm hoping that within this arc of 7 modules, we'll be able to cover all the fundamentals for you to then hopefully create wonderful projects in your studios and going forward. And by the end, you will have a complete parametric tower, and I will walk through how you can create a really nice presentation that could become a portfolio piece for you going forward. So my intention for you is to follow along with the tutorials that we will launch every Tuesday morning. And you're going to try things on your own. You're going to break things sometimes. You're going to experiment. But the way that the course is set up, it's set up in a modular format. So we're building on the knowledge from previous week. And this is how you can learn Grasshopper. So it is practice-based. It's going to require time, but it's absolutely doable. And the impact that it'll have in your design and the way that you will hopefully integrate technology in your future going forward is going to be unmatched. Trust me. So I'm really looking forward to working with you this semester. So let's get started.